Continuing in Chapter 7, Section 6, we are going to address Algebra 2 State Standard number 10, where students need to graph quadratic functions, and they may not be in standard form. We also need to determine the maxima, minima, and zeros of the function. That'll be apparent as we go through this lesson. And in this lesson, we're going to graph them in standard form, which is what we did in our previous episode in Chapter 7, Section 5, which is sometimes called a completed square form. And we're also going to do that in general form as well. We need to find the maximum and a minimum. General form looks like this: f of x, or think of it as y if you wish, equals ax squared plus bx plus c. Again, a cannot be 0. If the quadratic term is 0, we get a straight line. And for the completed square form, or what I'm calling standard form, f of x, or y if you wish, equals a x minus h quantity squared plus k. Again, a cannot be 0. Now, what are the maximum and minimums? We saw in the previous lesson that parabolas can open up or the parabolas can open down. One of those two things. Well, it makes sense if a parabola opens down, the highest point on the graph is its maximum. That happens to be the y value of the vertex. If the parabola opens up, the lowest point on the graph is the y value of the vertex, and we would call that the minimum, lowest point on the graph. So let's take a look at graphing this particular example. F of x is 2 times quantity x minus 3 quantity squared plus 1. So why don't we think of it as y for now, since you may be more comfortable with that. Since this 2 is a positive, as we learned in the previous lesson, that a is positive, parabola opens up. Absolute value of 2 is greater than 1, that we learned in the previous lesson, means my parabola is narrower than usual. Vertex is going to be the opposite of what's inside the parentheses, positive 3. Same as what's outside the parentheses, positive 1. Axis of symmetry is x equals the x value of the vertex. From there, I'm going to select 2 points that are on one side of the axis of symmetry or the other. To the right of 3, I find points like 4 and 5. If I wanted to go to the left of 3, I would find points like 2 and 1. But let's just go to the right of the axis of symmetry and use 4 and 5 for my x values. So plotting, we can see there's my vertex, 3, 1. There's my axis of symmetry. Yes, going to the right, for x values we get 4 and 5 that we're going to put in the chart of points. If we put 4 into the original equation, either one, 4 minus 3 is 1, 1 squared is 1, 1 times 2 is 2, 2 plus 1 is 3. And then if we put in 5, 5 minus 3 is 2, 2 squared is 4, 4 times 2 is 8, 8 plus 1 is 9. So let's plot those points. So there's the first point, 4, 3. And here's the point 5, 9, which is off my graph grid. And that can happen when you have a parabola that's narrower than usual. Alright, I've got the axis of symmetry, so that means I know the reflection of those 2 points that I calculated over the axis of symmetry that I'm highlighting in purple here. Through those points, I can draw the graph of my parabola. And we're ready to move on to example number 2. Now you'll notice the difference. Example 1 is something called standard form. Example 2 is something called general form. We know what to do when our parabola is in standard form. So what we need to do now are a few extra steps for example 2, and that's to take general form and convert it into standard form. The way we do that is the process of completing the square, like we learned earlier in the chapter as we were developing the formula for the quadratic formula. So let's start out, call it y for now, equals 3x squared minus 6x plus 1. We're going to complete the square. And what we did earlier this chapter was take the constant, move it to the other side, and we're going to do the same thing here. The only thing that's different, earlier we had 0 by itself, here we've got y by itself. So we've got y minus 1 is 3x squared plus 6x. I do not have a coefficient of 1 in front of x squared. Earlier in the chapter, just to factor and find the solutions, we divided everything by that. But in this case, let's just think of taking this number and factoring it out of my squared and my linear term, my quadratic and linear terms. So 3x squared divided by 3 is x squared. Negative 6x divided by 3 is negative 2x. And we're going to look to see what will go inside the parentheses to complete the square. What we've done is a variation of what we learned earlier by factoring out the 3 rather than dividing it out. In parentheses, I have a coefficient of 1x squared. So I can complete the square inside the parentheses doing what I call the Texas two-step. So let's take this 2 and do two things to it. We'll divide it by 2 and square it. That's the Texas two-step. So 2 divided by 2 is 1. 1 squared is 1. But be careful, that's what goes in parentheses. But we have a 3 in front of the parentheses being distributed all the way through. So by adding a 1 inside the parentheses, I really added a 3 to the right side of the equal sign, the right side of the equation. So to keep the equation balanced, I must add 3 to the left side of the equal sign as well. And on the left side, negative 1 plus 3 is 2. On the right side, leave the 3 alone. In parentheses, we have a perfect square trinomial formula we learned in Chapter 4. That factors as a square root of the first one, square root of the last one, sine of the middle term, quantity squared. Now to get it in standard form, all we have to do is get y by itself. So if we subtract 2 from both sides, now we've taken from general form and rewritten this equation for the parabola in standard form. And we're pros at this by now. So let's fill in some more information. That's positive, so it opens up. The absolute value is larger than 1, so it's narrower than usual. My vertex is positive 1, negative 2. My axis of symmetry is x equals 1. If I go to the right of my axis of symmetry, I can find points like 2 and 3 for x values. If I put 2, substitute 2 in for x, 2 minus 1 is 1, 1 squared is 1, times 3 is 3, and 3 minus 2 is 1. If we substitute in 3 for x, 3 minus 1 is 2, 2 squared is 4, 4 times 3 is 12, 12 minus 2 is 10. So now that we've calculated some points, let's plot our vertex and some of the other points like 2, 1, and our other points like 3, 10, which again, anytime my parabola is narrow, it's possible that it does not fit on my graph grid. It's a little bit stretched vertically. I didn't draw my axis of symmetry, but we can see where the mirror images of our calculated points are and plot them, which I color-coded in purple. Draw in the sketch, which I didn't bother going all the way up there. And now we need to consider something else that we can do with parabolas other than graph them. But in this last example, example 2, we converted from general form to standard form. Once we have it in standard form, we can go ahead and graph. So example 3, we need to do the same kind of process, but in addition to graphing, we need to find some other information like the domain, the range, the zeros, and the vertex. So let's start. Jump right in. Let's think of g of x. Just think of it as y for now. Let's rewrite this in different order and call it negative 3x squared plus 6x plus 6. That puts it in simplified polynomial order. Let's complete the square by taking the constant, moving it to the other side by subtracting 3 from both sides. Let's factor out the negative 3, and it's not that we're looking for a greatest common factor. It's whatever the coefficient of x squared is, that's what we're factoring out. So negative 3x squared divided by negative 3 is 1x squared in the parentheses. 6x divided by negative 3 is negative 2x. So in the parentheses, we have a coefficient of 1. We can complete the square here for a perfect square trinomial. Do the Texas two-step. So 2 divided by 2 is 1. 1 squared is 1. That's the number that goes inside here. But that's not what we added to the right side of the equal sign, because this 1 is being distributed by a negative 3. So we need to add a negative 3 to the left side of the equal sign to keep the equation in a state of equivalence. So negative 6 minus 3 is negative 9. Let's factor our perfect square trinomial in our parentheses. Take the square root of the first term, square root of the last term, sine of the middle term, quantity squared. And if we get y by itself, we'll have our parabola in standard form. So to do that, we'll add 9 to both sides. Now that our parabola is in standard form, it's a little bit more familiar to us. Since a is negative, our parabola opens down. Absolute value of negative 3 is positive 3. That's larger than 1, so my parabola is narrower than usual. My vertex is positive 1, positive 9. Remember to take the opposite of what's in parentheses and don't change what's outside the parentheses. My axis of symmetry is x equals the x value of the vertex, which is 1. So I'm going to select points like 2 and 3 to make my chart of points, since they're to the right of the axis of symmetry. If we substitute in 2, 2 minus 1 is 1, 1 squared is 1, 1 times negative 3 is negative 3, and negative 3 plus 9 is 6. If we substitute in 3, 3 minus 1 is 2, 2 squared is 4, 4 times negative 3 is negative 12, negative 12 plus 9 is negative 3. Alright, let's get to the plot. Here's my vertex, which is the point positive 1, positive 9, a little bit off my graph grid. Calculated points 2, 6. Calculated point 3, negative 3. The mirror images of my calculated points. Here's my axis of symmetry. I just didn't draw it in. Complete the sketch. There is our parabola. Opens down. That's narrow. Now, what is the domain? Well, although it doesn't look like it initially, if we were to continue to draw this, not only would my parabola go down forever, but it would also open to the left forever. Now, a narrower parabola would probably do that slower than a wider one. And it would open to the right forever. So eventually, I would be getting all the way out to negative x, very small numbers like negative 1,000, negative 1,000,000, negative 1,000,000,000. Eventually, my x values would be getting out positive 1,000, positive 1,000,000, positive 1,000,000,000, and positive and negative infinity eventually. So essentially then my domain is all real numbers for the x values. For the range, the maximum point is the y value of the vertex, which is 9. I do not have any values larger than 9, but I want everything including 9, and going down on the number line is smaller. So my range is a set of all y values such that y is less than or equal to 9. That's the conditions for the range. Now to find the zeros. And another reason why I didn't extend this graph, beside being difficult to draw on the graphics tablet, is I didn't want to give any hints to where it crosses the x-axis. Because to find the zeros means what happens when y is 0. Translation, where does it cross the x-axis? And another way of looking at that is my solutions. So to find the zeros, here's what we do. Just replace y, or g of x in this case, with 0, and solve this equation as we would solve any quadratic equation. A is negative 3, b is 6, c is 6. Put it into the quadratic formula. Simplify the quadratic formula. In this case, 6 squared is 36. Negative 4 times negative 3 times 6 is 72. 36 and 72 is 108. And the denominators, 2 times negative 3 is negative 6. Square root of 108, well, that could be the square root of 36 times the square root of 3. And the square root of 36 is 6. Looks like there's a greatest common factor in the numerator there of 6. So when we factor that out, which, by the way, excuse me, but I did that in my head, we're left with positive 1 plus or minus the square root of 3. You could divide this out. Negative 6 divided by negative 6 is positive 1. Plus or minus 6 squared to 3 divided by negative 6 is plus or minus the square root of 3. So it crosses the x-axis at 1 plus the square root of 3 and 1 minus the square root of 3. Those are my zeros. If we needed to identify that for our graph, of course, we would convert the square root of 3 into a decimal approximation, 1.732, and then that would tell us where it crosses the x-axis. Alright, let's look at another one. And in this one, we have the lovely distinction of dealing with fractions, but that's okay. So I'm going to take the constant, move it to the other side so we can complete the square and translate this from general form into standard form. 1/2 is not the greatest common factor, but whatever the coefficient of x squared is, we want to factor out. So 1/2 x squared divided by 1/2 is positive 1x squared. Be careful here. 3 divided by 1/2 is 6 times x. Some students make a careless mistake and we'll call this 3/2, but it's 3 divided by 1/2. Dividing by a fraction is multiplying by its reciprocal, and 3 times 2 is 6. Alright, now in the parentheses we've created a coefficient for x squared of 1. So in the parentheses we can do the Texas 2-step and complete the square. So 6 divided by 2 is 3. That 3 squared is 9. That's what goes inside the parentheses. But that 9 is being distributed times 1/2, as is everything else in the parentheses. So I really added 9/2 to the right side of the equal sign and need to add 9/2 to the left side to keep the equation in a state of balance. 9/2 is 18/4. Add that to 7/4, we get 25/4. Factor my perfect square trinomial as x plus 3 quantity squared. Get y by itself. And we've got our parabola in standard form from general form. We know the vertex, which is what they're asking us, is -3 and then -6 1/4. Now, I didn't write down, but if we look at A, it's positive, so my parabola opens up. If it opens up, that means my parabola has a minimum, and the minimum value is the same as the y value of the vertex. If this was -1/2, my parabola would open down. I would have a maximum, a highest point, and that would still be the y value of the vertex. All right, that's our second look at graphing parabolas.